Hello again, and welcome to another review session for your final exam in Calculus 3208, presented by CDLI, and we're rolling right along with more applications of derivatives here. So we're looking at another option for applications of rates of change, and this time we're talking about applications in the natural sciences. Wow, that's crazy stuff. All right, this is probably the most commonly cited application that I can think of for calculus in any sense would be these three sciences: physics, chemistry, and biology, which are probably also the three most commonly studied sciences in high schools. So with that in mind, the goal here is not so that you memorize how to solve any particular type of problem in any one of these disciplines. We're not here to learn physics, chemistry, and biology, but just to show you that once you understand the nature of rates of change and the ideas behind derivatives, then you can apply that to just about any situation where one variable is changing and it's affected by another. So here are some good applications in these three disciplines. So a survey of some applications that you can use for these. In physics, we've already seen when we talked about rectilinear motion, that's actually something that's related to mechanics. That's the kinematic side of mechanics. It also works for dynamics as well. But in physics, we can apply calculus to mechanics and fluid dynamics, electricity and magnetism, field theories, quantum physics, nuclear physics, and the list is really endless. Keep in mind that calculus really came about as a result of Isaac Newton trying to solve some problems related to physics that he couldn't solve with any other sort of mathematics. So the two kind of go hand in hand in terms of their inception that way. And also chemistry we've found some really great applications for calculus in the chemistry and its related fields over the years. So reaction rates are a big deal because anything that has a rate of change we can study in terms of calculus for sure. Chemical equilibrium is another one where calculus has some good implications. Density problems, we see a lot of those in calculus stories over the years. And physical chemistry, of course, anything that involves motion is going to have to deal with calculus as well. And in biology, sometimes folks think, well, it's only for the really mathematical sciences, so calculus is not important for biology, but that's not really true. Lots of applications in biochemistry, body mechanics, some population change things like we saw in a previous review session, and even some dynamic systems or interaction between different types of organisms. So calculus is really a universal language, and it's a discipline unto itself, so it's an important thing to study and to understand for its own sake, but also has some great applications in some other fields. So let's do an example from each of these fields of an application of some calculus, and then we'll leave you with one for your turn question. So here's the first one. In physics, and we'll get away from motion for a change. Haha, a change. Do something a little bit different this time. So what we're going to look at here is electricity. So the instantaneous rate of flow of electric charge past a point in a conductor is called electric current. And we use the letter I to represent that. Those of you who study physics will probably think of current I as being Q divided by T. Well, it is and it isn't. That's only on an average level. In fact, current can be something that's not consistent. It can be variable and change as a function of time. And so therefore, current has different values at an instantaneous level. So if we want to talk about current at an instantaneous level, it's actually dq divided by dt, or the rate of change of charge with respect to time. So if we think about this in units, it comes out to be measured in something called amperes, or amps, as you might know. And 1 ampere, or 1 amp, is actually 1 coulomb of charge. Everybody recognizes the name Coulomb, those of you that know physics. And that's going to be divided by coulombs per second of time. So 1 ampere of current is how much charge flows past a certain point in 1 second. So the quantity of charge in coulombs that passes through a particular surface is given by this function. So here, what we've done is we've been able to model in a particular situation. We don't need to know much about that situation other than we have a function that tells us how much charge we have flowing through a conductor at any given time. So we have to find the current in this conductor when time equals 1.5 seconds. So how fast is it flowing? Well, the calculus behind this is very simple. It's just finding the derivative of charge with respect to time that tells us about current. So this will be 3 times t squared minus 4t plus 6. So a simple polynomial derivative. So we need to find q prime at 1.5. So that's going to be 3 times 1.5 squared minus 4 times 1.5 plus 6. And of course 1.5 squared, 1.5 of 1.5 is 2.25. And then we're going to subtract 4 times 1.5, which is minus 6, plus 6. So these two terms will cancel, and we'll get 6.75. And so we have 6.75 amperes of current. So that's how fast, 6.75, look at that. Say one thing, write another, huh? So 6.75 amperes is how fast the current, or how fast the charge is flowing past that point at exactly this time. Let's look at another example. This time we'll go to chemistry. So in chemistry, chemical reaction, or in a particular chemical reaction, I should say, one molecule of each of the reactants A and B combine to form one molecule of the product C. So those of you that recognize chemical equations, and even if you did your Science 1206 course way back in grade 10, it doesn't matter if you haven't taken any chemistry since, you can still manage this. Two reactants are added together, and they make one molecule of a product. Just about the simplest chemical equation you can have. It says, if the initial concentrations of each reactant A and B are both 1 mole per liter, which we sometimes call molar, but if they're both 1 mole per liter, then it can be shown that the concentration of C, which is our product, is given as a function of time by C equals this equation, KT divided by KT plus 1, where K is a constant and time is measured in seconds. So we're going to treat K just like a number instead of a variable, of course, if it's constant. It says the reaction rate is defined as the rate at which the concentration of the product increases. So find the reaction rate at time t equals 1.2. So again, it's the rate at which the concentration of the product, which is C, increases. So that concentration, it's going to be increasing at a rate called C prime of t. Okay? So I have to find the derivative of my function that I had that represents my concentration. So this one's a little more involved. It's not a straightforward polynomial, but it's still not too bad. It's just a quotient rule with some simple a simple numerator and a simple denominator. So up top, I've got to take the derivative of KT, and that's going to be just a K, multiplied by the stuff on the bottom, which is KT plus 1. Okay. Then I have to subtract the derivative of my denominator, which is again just K, multiplied by what's upstairs, and that's just KT. And all of that business should be divided by KT plus 1 all squared. Okay, so if we put that together, we're going to have in the first term there K squared T plus K, and then minus K squared T all over KT plus 1 squared. So another quick simplification there, and we can see that these terms are the same but with opposite signs. So our first derivative then is going to be equal to simply K over KT plus 1 squared. And what we've done is we've taken the formula for the concentration of the product in our chemical reaction, and we've used it to write a formula for the reaction rate. So let's see. The rate of change of the concentration, or the reaction rate, we just found, so we want to evaluate that now and get it at C prime at 1.2. So we're going to take K, which we don't know, and divide it by 1.2 times K plus 1 squared. And so basically, that's about as much as we could do with that. Assuming K was a positive constant, then this will be a positive reaction rate. But there's not much else we can do to simplify that. So there it is, given in terms of K. So now you would know, based on whatever the actual constant is that is determined for this particular type of reaction, you can figure out the reaction rate just by plugging into that formula. Okay? So there's a little application to some chemistry. And now we'll look at one for biology. So this one has to do with the amount of glucose that's found in a person's bloodstream. Okay. So it says that amount is in part determined by their metabolism. Okay. So the higher your metabolism, probably the faster you're going to use up your blood sugar, I guess. So the mass of glucose in the metabolic experiment decreased according to an equation. Oh, we love it when you give us an equation. So here's our equation. It says where T is measured in hours and M is measured in grams. So M is the mass of the glucose, and T is the time that we're talking about since the start of this particular experiment, a metabolic experiment. So for people with diabetes, the rate at which the amount of glucose in the body is changing can be a crucial determinant of health. We all know that the level of glucose in a diabetic's bloodstream is important, but here they're talking about the rate at which that is changing. So if it goes up or down too quickly, that can cause problems as well. So for the given model, find the rate of change of the mass of glucose at time equals 1 hour after this experiment began. Okay, so another question that just says, what's the rate of change? And then we'll have to interpret what it means. Okay, so we want dm over dt. First of all, to get our rate of change, we're going to need a derivative. And this is a very simple function to differentiate. I almost said derivorate. So that's going to be 0.04 times t, because the 5 is constant, so that's gone. So there's our rate of change, and it says, find the rate of change of mass of glucose at time t equals 1 hour. So dm over dt at time t equals 1 hour is going to be negative 0.04 times 1, which will give us negative 0.04. And this is going to be in grams per hour. So what does that tell us? Well, it says that during this metabolic experiment, the mass of glucose in the person's bloodstream is decreasing by 0.04. It's decreasing because this is negative, of course, by 0.04 grams every hour. Now, that rate of change might shift around a little bit as time passes, but instantaneously, at exactly 1 hour after the experiment began, that's the situation that we're facing. Alrighty. So here's the Orator in question, and this one I cooked up to make a little bit more of a challenge for you in terms of the derivative that you actually have to take here. But it says a cylindrical water tank has a capacity of 5,000 gallons, and it's drained through a valve at the bottom of the tank. According to Torricelli's law of fluid dynamics, wow, that sounds cool, the amount of water remaining from a full tank that is drained is modeled by a function of time in minutes. Wow, here we go. Then it says find the rate at which the water is flowing out of the tank after exactly 20 minutes. Sounds similar to the other problems we had. And then you should be able to interpret what your answer means in the context of the problem. And so there's the solution for the Orator question, and also a little bit of a sentence to interpret what's happening there. So hopefully you're rolling through that stuff, and then we'll just do a quick highlight of all the details that we talked about in this session. So some of the things were, while there are innumerable applications of differential calculus in the natural sciences, there is one common theme among all of these things. This is supposed to say theme, not fees. Sometimes I think I forget how to spell on purpose, just so I can have some fun with it. But that should definitely be an M. All right. And the theme among them all is instantaneous rate of change. Without calculus, we can't get the instantaneous bit. Not perfectly anyway. We can only get estimates. All right. So using derivatives, what we can do is we can solve important problems related to electricity, chemical reactions, and even human body functions like we saw in these particular examples. Now, if you want a good sort of step-by-step method to tackle one of these rate of change problems, then basically, first thing you got to do is try to read and understand the problem. If you understand the context of the problem, it makes everything so much easier. Then you're usually just going to have to find the rate of change of the required variable. So take the derivative and plug in the value of the independent variable that you had. And then you have to interpret your answer in the context of the problem. So explain what it means, because let's face it, if you're hired as a consultant or something because you can do the math but somebody else can't, and then you can just give them a bunch of gobbledygook, they won't know what it means. But you have to interpret your answer in the context of the problem. That not only shows that you know what you're doing, but it helps anybody else out that you're trying to assist here. All right, hope that was helpful. So lots of different rates of change questions you could be asked. You never know what's going to come down the pipe on a test or an exam. But there you go. That's just a quick smattering of a few. Hope your studying is going well. And we're going to get into some harder applications of derivatives in the next few sessions of this stuff. So stick around and enjoy the ride.